This PhysioX has everything to do with the lab that you are doing tonight. Looking at membrane transport, what can move and what can't move. If solutes are found in unequal quantity across the cell membrane, if they can't move, what will? Water. So in the very first experiment, you were playing with dialysis tubing, just like you are tonight. Molecular weight cutoff means that there are tiny little holes in the membrane. If a solute has a molecular weight smaller than the whole number, then it can move through the membrane. Tonight, you're playing with a molecular weight cutoff that is much too small for sucrose to pass. Sucrose should not be able to get through the bag membrane. Molecular weight cutoff of 50 means the solute has to be smaller than 50 to get through. Molecular weight cutoff of 20 means the solute has to be smaller than 20. You get the idea. Your job for the lab exam will be to remember the 4 molecular weight cutoff tubes that we played with: 20, 50, 100, and 200. Your job will also to be remembering what 4 solutes we played with. We played with sodium chloride, urea, glucose, and albumin. That's not a long list. When we first started playing with a molecular weight cutoff of 20, did anything move? No. Everything was bigger than 20. So nothing was able to move through the membrane. Then we moved up to a molecular weight cutoff of 50. What moved? Sodium chloride. But wait, the molecular weight of sodium chloride is 58.45. Dissociation is the key. Sodium chloride does not stay as a molecule in water. It dissociates into 2 ions. Sodium has an atomic weight of 23, and chloride has an atomic weight of 35. Those numbers clearly are smaller than 50. Then we went up to a cutoff of 100. Sodium chloride was still able to move, but now another solute had the ability to diffuse. Which one was that? Urea. So you probably didn't know the molecular weight of urea, but from this experiment, you should know that it was bigger than 50, but less than 100. And that's the reason why it was able to diffuse. In fact, urea has a molecular weight of about 60. Then we went up to a molecular weight cutoff of 200. What now could move? Glucose. Glucose has a molecular weight of 180. Was albumin ever able to move? No. It is a huge protein. It has a molecular weight, something it's like 66,000 kilodaltons. Let's just say that's much too big for it to get through. This experiment actually is continued in another experiment later on in this exercise. And when we get to that second part, we're going to go to the board and I'm going to explain how I'm going to test you on the second set of experiments on your lab exam. There are only so many ways I can test you on this, and I've given you 4 examples on the board that we will go through together in just a moment. Are there any questions on activity 1? Okay. Well then, let's move on to activity 2. Activity 2, we were simulating facilitated diffusion. Facilitated diffusion is where the outcome is the same as simple diffusion. A solute is being moved from high to low. The process will continue to go until the same outcome occurs, which means you reach equilibrium. The way it's different, though, from simple diffusion is that in facilitated diffusion, there is a physical binding to the solute by the protein carrier. And this means that the number of carriers is the rate limiting factor. And this experiment got a lot of things right. For example, we built glucose carriers into our membrane. We built in either 100 or 500 or 700. We also use different concentrations of glucose. That's like changing the workload for those carrier proteins. The more concentrated, the more those proteins had to work. The longer it would take them to reach equilibrium, getting equal distribution of the glucose on both sides. So when we had 500 carriers and 2 millimolar glucose, well, we reached equilibrium. We equally distributed the glucose on either side pretty quickly, but it was even faster when we had 700 carriers. If this building was burning down and we were trapped in here, would you want them to send in 3 firefighters or 30? Who said 3? Because you're waiting to the end then. I'm hoping for 30 because then there's one for all of us. And we'll get out faster. We want to equilibrate outside of the building. Thank you very much. When we jumped up to 8 millimolar, we increased the workload. It took a little bit longer to reach equilibrium with the 500 carriers compared to when we only had 2 millimolar. And when we jumped up to 700 carriers, even though there was a greater workload, it was faster than when we had 500. More firefighters to come rescue us. Well, then we went up to 10 millimolar. Now we're really increasing the workload. Now we dropped the number of carriers down to 100. That's crazy. And what happened? What happened? Were you mad as hell? Did you get mad because the system timed out on you? Did you throw your book across the room and say, "No, Phys Ex, I want to see it finish"? Liars. Didn't you want to go in and tinker with the time and say, "Just give me another minute"? Because if we could reset the time and give us more time, we would have seen the system reach equilibrium. It timed out on us. The system timed out on us before we reached equilibrium, which meant we had hit transport maximum. If only 3 firefighters come to rescue us, that means only 3 of us can move at a time. And that means the rest of us, who's ever the last group, is waiting even longer to be rescued. Does that make sense? Okay. Then in the very last experiment, we went back to 700 carriers. We dropped back down to 2 millimolar glucose, but we sprinkled in sodium chloride. As if to say, now what are you going to do, glucose carriers? And the glucose carriers looked at us and went 2 middle fingers up saying, don't care. My job is only to move glucose. I don't care what else you put in here. It doesn't get in my way. I grab the glucose that I need to move. Are there any questions on that? No? Okay. Look, this Phys Ex goes right along with our first PowerPoint, our first lecture for Unit 2. I went through membrane transport, and you all sat there going, yep, diffusion, osmosis, facility. I've heard this all before. And I said, this is arguably your 6th time you've heard it. Now let me prove to you why you care clinically. And you all sat there and went, yep, I got it. Transport maximum, no problem. Guaranteed you don't. On lecture unit 2, I give you descriptions of some solute moving, and you have to match it to the kind of membrane transport it uses. And that's where you start sweating bullets like, I thought I knew this. And yet the examples I give you on the test come straight from the PowerPoint. It's not even new stuff that I'm making up. It's right there. For example, and I warned you about this one, I'll warn you again. If sodium voltage gated channels suddenly open, what gets to move through them? Good. How does it move? Diffusion. It's simple diffusion. Yet those voltage gated channels open during an action potential. And the word action makes students think, oh, active. I'm using energy, cellular energy. No, you are not. And do you remember I warned you about that one, that very one? And you all went, right then, I'm going to remember this. I bet you've already forgotten it, which is why I'm reminding you again. Okay, in the next activity, it is a continuation of activity number 1. We are still using membrane cutoff dialysis tubing. The only difference is we're not playing with urea in this one. That's okay. We still could have played with urea because we know from the first activity when urea can move and when it can't. So in the first activity, the first experiment, I should say, we had a molecular weight cutoff of 20 and we were playing with sodium chloride, 5 millimolar. That's written down in the instructions, but I encourage you to write that down in the column on the chart in front of you. It's important to remember what we played with. The concentration matters. So we played with 5 millimolar sodium chloride with a molecular weight cutoff of 20. Can sodium chloride move? No. So what did? And what we were doing in this experiment, we were applying pressure onto a piston. We were trying to oppose the water coming into that side where the sodium chloride was to dilute it. We were trying to oppose it. And we had to push down with a pressure of 170 millimeters of mercury. That's how hard we had to push. And then in the next experiment, we doubled the amount of sodium chloride. Well, what happened to the force we had to push down on? What happened? How hard did we have to push? Twice as hard. Twice as hard. So the pressure on the left, Matt, because I heard you say 0. The pressure on the left is where the water wanted to go. The left beaker had the sodium chloride. The right beaker had water. The sodium chloride could not move. So water went from the right beaker to the left, or tried to, and it was the left side where we were trying to oppose that.
Because on the results sheet, I must have got it wrong or something because it was said 0.
Was it crisscrossed applesauce? Was your right beaker then?
Yes. I don't know because I got a decimal for the diffusion rate. That's correct.
Okay, are you on chart 3?
Yeah. So I must have done this wrong.
Oh, so okay, you're looking at diffusion rate. Hold on. Okay, I got you. Look at me. There was no diffusion of sodium chloride.
Okay.
What we're looking at is the pressure.
Oh, okay.
Because the sodium chloride could not move, there was no diffusion of the solute. What did move? Water. In this second experiment, we doubled the amount of sodium chloride. This resulted in a doubling of the amount of pressure we had to push down to oppose the water from moving. I know. In the next experiment, I did. It's okay. In the next experiment, we used a molecular weight cutoff of 50. Was sodium chloride able to move now? Yeah. There was no osmotic pressure. If the solute can move, it will. We didn't have to push on the piston at all because the solute was able to move. Okay, now Phys Ex did something really interesting, and I love it. I love it, and you missed it. You missed it, guaranteed. We went to glucose, and we used a molecular weight cutoff of 100. Can glucose move through that tubing? No, so what will? Did we have to apply a pressure? Yes. What was the concentration of glucose that we used? 8 millimolar. What was the pressure we had to apply to stop the water from moving? It was 136. Here's my challenge. I wish they could have kept it consistent with the sodium chloride. I wish they would have. Why 8? Why couldn't they have used the same concentration for glucose as we had just done with sodium chloride? Why not 10? Why not 10? I want to know right now, if we had played with 10 millimolar glucose, tell me right now the pressure you would have to apply. Tell me right now. It's right there in front of you. There are 2 ways you can answer this. And I've already tested you on it. It was your chemistry test. Hell, the problems were in the first 20 pages. Did you delete that neuron? Did you donate your brain to a friend? Call the friend back and say, I need the brain back. I like to tease my husband with that. At any given time, I say, we're starting a chore. I'll say, do you have the brain? Because you need to call around. Get the brain. I have this sexist. It's sexist. I'm admitting it. But in my house, that's what I'm basing my knowledge on, from my observation in my house, okay? In my house, I have this idea that all of the XY chromosome individuals share a brain. And at any given moment, they don't have it. So whenever we're about to start something that is problematic, I say, you need to call around and get the brain back. Please get the brain back. Again, this is based on my observation. I understand that was very sexy, my observation. For example, if I tell Honey to go outside and hedge the shrubs, he gets an extension cord. He gets the little shrub clippers. It's in the extension cord, goes over to the hedge, starts trimming, going along, which sounds fine, right? What you don't know is that the extension cord is going across the pool. Phone the friend for the brain. If we played with 10 millimolar glucose and not 8, tell me what the pressure would be. Look, it's right there. How did you get to that? What did you do?
I divided 136 by 4, then you would know how much is 2 liters of concentration, and then I added that on.
Okay, I know what he said, and I am going to take that and I am going to massage it just a little, because I understand what you did.
It's rough.
No, I know what you did. You're fine, and your answer is correct. Our pressure doubled when we doubled the sodium chloride concentration, didn't it? It's a direct relationship, isn't it? So do you remember in your chemistry test, you did these problems? Oh yeah. You could have put 8 over 136, 10, and solved for y2, couldn't you? That's one way to answer it. Yours was another way. And there's still yet another way, and it was still tested in that chemistry test. Let me prove it to you. You ready? Are you ready? Look at the first experiment we did with 5 millimolar sodium chloride. Same chart, chart 3. Same chart. 5 millimolar sodium chloride. Millimolar, Rhiannon, millimolar. What does sodium chloride do in water? So tell me the milliosmoles. So 2 times 5 is 10. So we were playing with 10 milliosmoles, weren't we? We applied a pressure of 170. I said challenge. Let's say we were playing with 10 millimolar glucose. I said the answer for the pressure is right in front of you. Does glucose dissociate? So 10 millimolar glucose is the same as 10 milliosmolar, correct? If a particle cannot move, water will. Water is only concerned about the number of particles, not what they were. So if 10 milliosmol of sodium chloride, we pushed 170, then 10 milliosmol of glucose, we're also going to push 170. Then, in the next one, we put glucose, 8 millimolar again, on both sides. We used a molecular weight cutoff of 100. Well, then it's balanced, isn't it? Glucose can't move, but it's balanced on both sides. So is water going to move? No. No. We had a diffusion rate of 0 because glucose couldn't move. And even if it could, isn't it already at equilibrium? We still wouldn't have seen any net shifting of water. And then we went to 8 millimolar glucose with a molecular weight cutoff of 200. Great. Can glucose move now? Yep. Did we have to press on our piston? Nope. And then in the last one, we had albumin on one side, glucose on the other, and we had a molecular weight cutoff of 200. Huh. Can albumin move? Can glucose? So visualize this. I have albumin on one side. I have glucose on the other. Albumin can't move. It's stuck. Glucose can. Some of the glucose is going to move from this side to that side until glucose reaches equilibrium. Let's say 4 on one side, 4 on the other. Now we have 4 millimolar glucose plus the albumin. So which side has the highest osmotic force? The side where albumin and the glucose now is. Make sense? I don't think it does. So here we go. Up on the board, you are seeing, and I will take a picture of it for this video when I'm done. I just don't want to move my camera right now. You are seeing scenarios. On your lab exam, I don't draw the pictures, I use the words. The words will read like this. You have 2 beakers. On one side, you use 5 millimolar sodium chloride. On the other side, you use 5 millimolar glucose. Lower this for you. Watch your fingers, sweetie. The 2 solutions are separated by a molecular weight cutoff of 20. Now these are the words. What's stopping you from making the picture? See better? Nothing. You're allowed to draw on your test. You know this. Okay, so you set up your system. First question you always ask yourself, can any of these move? Can any of them move? No. Sodium chloride can't get through a molecular weight cutoff of 20, and neither can glucose. Okay, if neither one can move, now you need to ask yourself, do I have equal particles? Do any of the solutes dissociate? That's another way of asking that. Well, sodium chloride does and can. So that's 10, isn't it? 10 milliosmoles. So this is in molar, not milliosmoles. Millimolar is different than milliosmoles. So this is 10 to 5. which side will have the highest osmotic force? Sodium chloride, and that's what you're going to mark on your test. Here's another scenario. 5 millimolar sodium chloride, 5 millimolar glucose. Molecular weight cutoff of 50. First question, do any of these move? Which one? Good. Whatever side has a solute that can't move, then that's the side that water goes to. If the solute can move, it will. If solutes cannot move and they're found in unequal quantity, then what will move? Water. So look, let's color this in. Sodium chloride will diffuse and will reach equilibrium. The glucose cannot. It stays put. All you have to do now is count the number of particles. Clearly the side on glucose has the greater number of particles. That's where your osmotic pressure will be. Here's another one. Molecular weight cutoff of 200. First question, can any of these solutes move? One? Both? Then done with the question. There is no higher side for osmotic pressure. You're done. No difference. No net shifting of water. Last one. 5 millimolar glucose on one side, 5 millimolar albumin on the other, molecular weight cutoff of 100. The same first question. Can any of these move? See, this is part of your responsibility to remember what could move and what didn't. Glucose can't move. Albumin can't move. Neither one moves. Okay, that brings us to question 2. Do either one of them dissociate? No, so they have the same number of particles. Will there be a shifting of water? No, done with question. Be ready to answer questions like this with glucose, sodium chloride, albumin, and even urea, the one that we played with in the first experiment. Urea does not dissociate. So out of those 4 solutes, what's the only one that we played with that dissociates? Sodium chloride, thank you. Okay? Okay. If there aren't questions on that, I'll move on to the next one. Okay. We did not do activity 4, but we did do activity 5. Now, I am a person where I like to do everything with my hot little hand and write in my book. I see a lot of you that did it online and on the computer and you have all your data saved, but I like to write things down. I like to take notes. Phew. Thank you. All the other experiments we just talked about, wasn't it convenient that they gave us charts to fill in? It was awesome. Not so for this one, was it? There was nowhere to fill in your data. Nowhere for those of us who like to handwrite it. And the little chart I did have in the picture on page 11, I actually tried to fill that tiny little chart in the picture. Do you know that we actually did 5 different experiments in that activity? 5. It's easy to lose track if you didn't write it down like I like to write it down. 5 different experiments, and they were all spot on. In the very first experiment we did, we had sodium chloride on one side, potassium chloride on the other, but not equal amounts. We had 9 millimolar sodium chloride on one side and 6 of potassium on the other. What's that ratio? 9/6. 3:2. Huh. Why? The sodium-potassium ATPase moves 3 sodium across the membrane for every 2 potassium that comes across the other way. That's a 3:2 ratio. Has to be that way. We built in some sodium-potassium pumps And we went, pring, we sprinkled in some ATP. That's the energy source. We're looking at primary active transport. And the goal was to have the pump move all the sodium over this side and all the potassium over to this side. And because it's 3-2, all of it should be moved. And it didn't happen. We didn't get it moved to completion. Why? We ran out of ATP. That's the problem. We ran out of the energy source. Okay, then in the next experiment, we remedied that. We added more ATP. And when we did that, we got all of the sodium moved and all of the potassium. They were swapped to the other sides of the chambers. Gold star for us. Phys Ex said, hey, don't get too cocky now. Let's try something else. Now, we put water on one side, sodium on the other. We added enough ATP. Nothing happened, did it? Nothing happened. Why? That sodium potassium ATPase, if it could talk to you, it would say, it's all or none with this moving thing. I need 3 sodium this way, 2 potassium that way. If my seats aren't loaded with 5 ions, 3 sodium, 2, I'm not moving a darn thing. It's not worth the energy involved. You either have me loaded up or you don't. And if you don't, I'm not doing anything. There's no half-assing it. So nothing got moved. Then in the next experiment, we did something very interesting. In the next experiment, we actually went back to our sodium on one side, potassium on the other, and we increased the number of pumps. We put in more ATPases. And what happened? We moved the sodium from one side to the other, the potassium to the opposite side, just like we did in experiment number 2. But it happened faster, didn't it? It was the number of pumps that was the rate limiting factor. Are you hearing that? Not the ATP. It's the number of pumps that's the rate limiting factor. Because in experiment number 4, compared to experiment number 2, the concentrations of the chemicals were the same. The amount of ATP we gave was the same. The only thing that was different was the number of pumps. And in the 4th experiment, we moved everything much more quickly. That's because we had more taxi cabs, more firefighters to come rescue us. Then in activity 5, this is something that we've already seen before. Back in the second activity. In the second activity, if you remember, we were playing with glucose carriers, weren't we? And we sprinkled in sodium chloride, and I said the glucose carriers could care less. They're focused on the glucose. Well, this was the same experiment, except that we were using sodium-potassium ATPases, sodium-potassium pumps. We had the sodium and the potassium. We had equal amount, well, the right amounts of them, 3-2. We had the ATP, and we sprinkled in glucose. And the ATPase was like, I don't care what else you put in here. Not my monkey, not my circus. I deal with sodium and potassium. That's it. Nothing else will distract me. Does that make sense? Okay. Well, then I will stop there after I take a snapshot of the board. You all, how about you take your measurements, and when everyone's done, we'll go over the muscle Phys Ex, also prep you for the quiz, and then you'll take the quiz, okay?